Welcome back. Today, we're putting on our hard hats and stepping right into the shoes of a civil engineer to look at a truly fascinating challenge. We're going to break down the mathematical and theoretical blueprint of unlined alluvial canal design. This explainer is built specifically to give civil engineering students, and really anyone fascinated by large-scale hydraulic structures, a clean step-by-step look at exactly how we safely channel massive volumes of water through the earth. All right, let's dive right into this.
So here's our roadmap for this explainer. First, we'll cover irrigation water demand. Second, we'll get into Lacey's regime theory. Third, we'll walk through step-by-step canal design. And finally, we'll wrap up with seepage and structural safety.
All right, part 1. Irrigation water demand, the requirement. You know, before a single shovel even hits the dirt or any cross-sections are drawn up, an engineer has to answer one really fundamental question. Exactly how much water do we actually need to deliver? To answer that, we've got to establish our foundational vocabulary, namely duty and delta. Duty is essentially the irrigating capacity of your water. It's how many hectares of land can be continuously irrigated by 1 cubic meter per second, or 1 cumac, of water, over the entire base period of a crop. Delta, on the other hand, is the total depth of water required for that crop to safely reach maturity. And hey, these aren't just abstract numbers on a page. They are directly tied to actual agricultural survival. So how do we put those definitions to work in the real world? Well, to find the exact discharge required right at the head of the canal, you take the total area you need to irrigate, say for a seasonal kharif or rabi crop, and you divide it by the duty. But we have to live in reality, right? Water inevitably evaporates and seeps into the ground as it travels. So we absolutely must add our transmission losses to that fraction. This simple, elegant formula is the starting point for our entire canal design. Moving right along to section 2, Lacey's regime theory, the physics. Now that we know our required discharge, we've got to understand the physics of water interacting with unlined soil. Enter Lacey's regime theory. Gerald Lacey made this brilliant distinction regarding canal stability. He noticed the canals actually go through phases. First, there's the initial regime, where the canal might appear totally ideal, but it's deceptive because the width actually keeps varying. Then there's the final regime. This is where the depth, the wetted perimeter, and the bed slope all continuously adjust themselves until the channel reaches a state of true dynamic equilibrium. It's like a giant self-correcting puzzle. And the absolutely crucial point here is that Lacey's mathematical blueprint only applies to this final, perfectly stable regime. But getting to that final regime, that requires a pretty strict set of ideal conditions. First off, the channel must have a constant discharge. Furthermore, the flow has to be on coherent alluvial soil. What that means is the soil is loose enough that it can be scoured by the water just as easily as it's deposited back onto the bed. These conditions are the core assumptions that make all of the upcoming math possible. Let's just slow down here for a second, because this is a real game changer. Lacey introduced a crucial metric called the silt factor, denoted as F, which equals 1.76 times the square root of D, where D is the average grain size. Unlike the engineers before him, Lacey recognized that eddies, the swirling currents of water coming from the sides of the canal, not just the bottom, matter immensely for keeping silt suspended. Because of that, his critical silt factor is driven entirely by the physical size of the soil brains. However, as every engineer knows, theoretical models are usually just practical approximations. Lacey's theory definitely has its drawbacks. For starters, the equations are entirely empirical, meaning they're based on real-world observation, not pure fundamental physical laws. Also, relying on a single factor F really isn't adequate to capture all the complex silt characteristics. He didn't differentiate between silt grade and silt charge, and honestly, the actual concentration of the silt is completely excluded from the model. Pretty crazy, right? But despite those theoretical limitations, Lacey's formulas are still heavily relied upon in practice today. Which brings us to the million-dollar question. Equipped with our required discharge and our silt factor, how do we actually dimension this final regime canal? That takes us perfectly into section 3, step-by-step canal design, the application. All right, time to look at the exact math used to build the canal. When we look at these formulas, notice how our two knowns, discharge, or Q, and silt factor, F, drive absolutely everything in this sequence. Step 1, they calculate our velocity. Step 2 uses that velocity to give us our hydraulic depth. Step 3 scales our cross-section, which gives us the area and wetted perimeter. And finally, Step 4 determines our bed slope. This right here is the master algorithm of canal geometry. Now, in nature, a true regime canal naturally carves itself into a semi-elliptical shape over time. But excavating that perfectly in the real world, That's incredibly difficult. So for practical design purposes, we make an assumption. We dimension the canal as a standard trapezoidal cross-section. We typically assign a side slope of 0.5 horizontal to 1 vertical. This nice little shortcut allows the math to translate into a diggable reality. Okay, so we've successfully designed our canal channel. Awesome. But water is relentless. We have to shift our focus drastically downward, right beneath the visible surface. What exactly happens to the water that inevitably percolates underneath our related hydraulic structures, like weirs and barrages?
Which leads us to our fourth and final section, seepage and structural safety. This is where we learn how to prevent the massive concrete floors of our hydraulic structures from literally rupturing under the hidden upward pressure of groundwater. The foundational concept here is Bly's creep theory. Bly proposed that water percolating through the subsoil basically follows the exact outline of the foundation's base. The total path this water travels is called the creep length, represented by L. According to Bly, the total hydraulic head is lost uniformly along this creeping journey across the horizontal width and down around every single vertical cutoff or sheet pile. To keep the structure safe from what we call piping, which is a scary scenario where water erodes the soil right out from under the foundation, we have to maintain a safe hydraulic gradient, and that depends entirely on your soil type. For example, a fine micaceous sand requires a really high coefficient C of 15, meaning you need a very long creep length to safely dissipate that water pressure. But a stiffer loam soil, that only requires a coefficient of 5 to 9. But engineering didn't stop with Bly. Enter causeless theory, which is a much more rigorous and accurate approach. Kozla realized that water doesn't just strictly hug the foundation outline like a shadow. He introduced the method of independent variables. This is a brilliant method that takes a complex composite weir foundation and splits it up into standard, simple forms, like a flat floor with a single sheet pile, that can actually be solved using analytical mathematics. And one of the absolutely most critical outcomes of Kozla's work is the calculation of the exit gradient. When we calculate this, we see the gradient is heavily dependent on the seepage head and the depth of the downstream cutoff, denoted as D. Keeping this exit gradient below the critical threshold for the local soil is the ultimate test of whether your structure will stand strong or be completely destroyed by piping. Let's talk about the massive real-world stakes here. If the downstream cutoff depth, D, is 0, meaning you just forgot to install a vertical sheet pile at the end of your floor, the exit gradient literally hits infinity. Mathematically and physically, an infinite exit gradient means immediate, catastrophic structural failure. You absolutely, without a doubt, must have that downstream barrier. Ultimately, what we're looking at here is the great engineer's balance. As an engineer, you're constantly walking a tightrope. On one hand, you have to design the subsoil foundation to keep upward hydrostatic pressures low enough to prevent the floor from rupturing. But simultaneously, you have to keep the physical thickness and therefore the immense cost of that concrete floor to an absolute minimum. It's an incredible optimization puzzle. Which leaves us here. We've traced the entire path, from calculating agricultural water demand, working through Lacey's regime equations, all the way down to the structural safety of the foundation against groundwater seepage. But remember Lacey's limitations that we talked about earlier? It leaves us with a pretty provocative thought. Will future engineers and empirical models finally conquer the unpredictable, dynamic nature of silt concentration that our current theories still struggle to capture? It's a massive challenge just waiting to be solved by the next generation of civil engineers. Thank you so much for joining me on this explainer. Stay curious and keep learning.